Hello James! Welcome back to a series. In this video, we are going to discuss previous year BITSAT questions from the chapter of dual nature of radiation and matter, which says waves are matter and matter is in fact a wave. Yeah, that is how it's going to be today. Let's begin today's class. So question 1 and 2 over here, questions from the super easy category. Okay, so let's dive straight into it. Question 1, the number of photoelectrons depends on. Okay, so come on, this is a simple one. You should be ready with your answer in 3, 2, 1. Okay, the correct answer over here is option B. Okay, the number of photoelectrons depends on the intensity of radiation, right? You'll know this for a fact that number of photoelectrons is directly proportional over a wide range to the intensity of radiation. Okay, or you can also think about it in this way that when you increase the intensity of radiation, the photocurrent increases, right? Why does that happen? That happens because the number of photoelectrons also increase. Okay, so the photocurrent increases because the number of photoelectrons increased. So the thing that I want to say is the number of photoelectrons depends on the intensity of radiation. Okay, it does not depend on the frequency. The frequency just determines the kinetic energy of the photoelectrons. Okay, so the number of photoelectrons only depends on the intensity of radiation. So option B is the correct choice over here. Let's come to question 2. Okay, in question 2, particle which has a rest mass of m naught, it is moving with a velocity equal to that of the speed of light. The velocity is equal to c. Okay, c is the speed of the light. Okay, you are supposed to find the de Broglie wavelength of the particle. Okay, yeah, that is how you pronounce that. So yeah, find the de Broglie wavelength of this particle. Okay, let me help you. Option A is incorrect. Okay, did I help you? No. Okay, so let's solve it. Okay, so your de Broglie wavelength is given as lambda is equal to h by mv, right? Mv, momentum, p. Okay, so now here the mass which is placed, this is not rest mass, this is relativistic mass. Okay, relativistic, how do you spell that? Relativistic mass. Okay, so you have to consider your general theory of relativity in order to find this mass. Okay, you have to find the relativistic mass, which is given as the rest mass divided by the Lorentz factor. You'll know this, it's 1 under root of 1 minus v square by c square, where v is the velocity of the particle and c is the speed of light. Okay, so let's find the relativistic mass over here, which we want to substitute over here, and then we'll get what is the de Broglie's wavelength. Remember, this is rest mass, m naught. Okay, so let's find the relativistic mass. So when you substitute c over here in place of v, okay, the speed of the particle in our case is c, right? It is equal to the speed of light. So when you substitute c over here, it will be c square by c square, right, which is 1. This will be 1 minus 1, 0, so under root 0. Okay, so basically a 0 in the denominator. I hope you were able to follow me. So a 0 in the denominator means that term is infinity. Okay, so this mass is infinity, which was very obvious. A particle traveling at the speed of light will have mass equal to infinity. Yeah, that's one of the general results of your general theory of relativity. Okay, so basically the mass of this mass is infinity. Okay, so your de Broglie wavelength lambda, so you'll have infinity in the denominator, right? So which means the de Broglie wavelength will be 0. Okay, so option B, 0, is the correct choice over here. Okay, so yeah, that's all from the super easy category, I guess. Let's move to the easy category now. So question 3 over here, a small correction, we are still there in the super easy category. Okay, so this is a question from 2011. In this question, the energy of photons is 10 eV. Now what is this eV? Pokemon? No, it's electron volts, right? So energy of photons is 10 electron volts. You are supposed to find the momentum of this radiation, right? Photons. So radiation, find the momentum of this radiation. Now it's a easy job. What formula will you use? You'll use P is equal to E by C, right? The momentum of the radiation is given as energy divided by the speed of light, right? So first of all, where does this come from? Okay, we'll derive it in some way. So we can write your de Broglie's wavelength as h by p, right? From this we can write p is equal to h by lambda. Okay, for those who don't know how does this come, okay, so we are deriving it over there. Okay, so we'll multiply c on both the sides, so pc gives us hc by lambda. This is nothing but energy of radiation, right? So pc gives us energy of radiation, and your momentum will be given as E by C. Okay, so that is a small derivation for it, but anyways, you should know this for a fact. Also, you learn it in electromagnetic waves that energy of the radiation, momentum of the radiation is energy by C, right? So let's just substitute the values now. 10 electron volts. Now here you can see everything is in SI system, right? So convert that to joules, okay, that is energy. So convert that to joules. How do you do that? So multiply it by 1.6 into 10 to the power minus 90, right? 1.6 into 10 to the power minus 19 joules is equal to 1 electron volts. Okay, so in order to convert electron volts to joules, you have to multiply this factor, okay, and divide this by 3 into 10 to the power 8. So that will give you 16 by 3 into 10 to the power minus 27, right? 10 to the power minus 27, 16 by 3. Yeah, it will be 5.33. So 5.33 into 10 to the power minus 27. Okay, option D, 5.33 into 10 to the power minus 27 kg meters per second. That is the correct choice over here. Okay. Now I was off on YouTube for the last week. I was not there for the whole last week. I didn't film any videos. So if you do find me crazy today, it's because of that. Okay, I have lost the habit of doing it. So if you do find me crazy or off track, do enjoy that version of me. Okay, that is what I can say. Next question. So question 4 over here, the bar has been raised. This is a question from the easy category now. Okay, so in this question we have a plot of stopping potential versus frequency. You are supposed to find the value of AB by BC. Okay, find the value of AB by BC. Here you have your options, you can give it a try. Okay, now if we consider this angle as theta, AB by BC, you can see that it is nothing but tan theta. Right, AB by BC will be nothing but 10 of this angle, AB by BC, opposite upon adjacent, right? So we are supposed to find, in a way, we are supposed to find the 10 of this angle. Now 10 of this angle will give us nothing but the slope of this line, right? So in a way, they are asking you for the slope of this line. Okay, so you are supposed to find AB by BC, which is nothing but tan theta. Tan theta will give us the slope of that line. So find the slope of this graph. Okay, so find the slope of this plot. That is the reduced form of this question. Okay, so here some of you might directly know it, that the slope of stopping potential, if you have a plot of stopping potential versus frequency, the slope of the line on that graph will be h by e, right? So option C, h by e, will be the correct choice over here. Anyways, I'll go ahead and show how this is so. Okay, so we'll use the golden equation over here, which we are supposed to know in this lecture, in this chapter, which is kinetic energy is equal to the energy supplied minus the work function. Okay, your Einstein's photoelectric equation, or more specifically, it's the maximum kinetic energy equals energy supplied minus the work function, right? Now you can write this kinetic energy in terms of stopping potential. You can write it as EV naught, right, where V naught is the stopping potential and E is the charge on electron. Okay, so more about stopping potential in the next question. Okay, we'll come to that. So now you remember that kinetic energy can be written in the form of stopping potential, in the format of stopping potential as EV naught. Okay, let's do it now. Energy supplied can be written as H into nu. Okay, H nu equals H nu, where nu is the frequency of the radiation, and here work function can be also written as h into nu naught. Okay, nu naught is threshold frequency. I hope you are familiar with all these terms. Okay, so your stopping potential V naught will be given as h by E nu minus h by E. So I'm taking this E to the other side into mu naught. Okay, now you can compare this with y is equal to mx plus c and you'll get your answer. Okay, you can see that y is equal to mx plus c. Okay, you can see that V naught is on the y-axis, right? So stopping potential on the y-axis, and here x is the frequency on the x-axis. M is this value, right? M is nothing but the slope, and that is what we were supposed to find, right? M is the slope, and slope is h by E. So h by E is the correct choice over here. Okay, and C is this value minus h by E mu naught. Okay, anyways, we are not bothered about that. Here the slope is h by E. So yeah, that is what we were supposed to find, right? So option C, h by E, is the correct choice over here. Okay, so next question on stopping potential, it will clear all your doubts regarding stopping potential. Okay, so let's move to the next question now. So question 5 over here. In this question, you have used a radiation of wavelength 300 nanometers on a metal which has work function is equal to 2.54 electron volts. Okay, you are supposed to tell the stopping potential in this case. Find the stopping potential in this scenario over here. Okay, so again the same thing which was there in the previous question. We are just going to exploit that. What was that? The golden equation, right? So kinetic energy maximum equals E minus phi, right? So kinetic energy maximum, you can write it in terms of your stopping potential. It will be E into V naught, right? Charge on electron into V naught, and here E minus phi. E is the energy of radiation. You can write it as hc by lambda, and it is either h nu or hc by lambda, right? And work function, we already have the value, we'll substitute it in the next step. Okay, now I'll explain why this maximum kinetic energy is EV naught. For those who know it, can directly skip some seconds of this video, RIP watch time. Okay, so yeah, I'll try explaining that. So kinetic energy maximum, so that will give you a better idea of what stopping potential is. Okay, so kinetic energy maximum is equal to EV naught. Why is this so? Okay, so this basically comes from your work energy theorem, which says that change in kinetic energy. Now it's noteworthy to remember that this kinetic energy is of the photoelectrons, right? Obviously. Okay, so change in kinetic energy is equal to the work done. Okay, work done by all the forces. This is work energy theorem. Okay, now what is the idea of stopping potential? The stopping potential means that you have to create a potential so that no photocurrent flows. Okay, you have to create a negative potential with respect to the positive plate so that no photocurrent flows. Okay, and when will that happen? We have to just avoid the photoelectron with maximum kinetic energy from reaching the other plate, right? That is the basic idea. Okay, if you avoid the photoelectron having maximum kinetic energy from reaching the other plate, then of course no photocurrent will flow, right? Why does current flow? Because an electron flows from one plate to the other, right? From cathode to anode, right? Or anode to cathode. I don't know the polarities, sorry. Okay, so yeah, so the idea is to avoid the photoelectron with maximum kinetic energy to reach the other plate, right? So what do we have to do? We have to make the kinetic energy of the photoelectron, the maximum kinetic energy of the photoelectron should be spent in the work done against the potential. Okay, so that is the whole idea of stopping potential. You waste all the kinetic energy of your photoelectron in doing work against the potential. Okay, and it does not mix up to the other plate, and that's why there is no photocurrent. Okay, I hope you got the idea. Anyways, even if you didn't get it, this is what you need to know. Okay, kinetic energy maximum is E into V naught. Okay, yeah. So yeah, this is equal to the work done. Now I can show that work done will be equal to, you can write potential as W by Q, stopping potential as W by Q. Q here, the charge is your electron. So you can write your work done as E into V naught. Okay, so this kinetic energy, the loss in the kinetic energy, finally it becomes 0, right? So basically you can write the maximum kinetic energy will be equal to EV naught, right? Finally, final kinetic energy is 0. Okay, so now let's get back to this EV naught. Okay, so we are supposed to find the stopping potential. Okay, the story is over. EV naught. Okay, it's C by lambda. Now one more trick I'll give you. Whenever you have this sort of things, if you want the answer in electron volts, you can use this. You can use the value of Hc as 1240. Okay, and place lambda in nanometers. Okay, use your Hc as 1240. This is a short trick. Okay, you might know this from your reference book. Okay, so it will be 1240 divided by lambda in nanometers. That will give you the energy in electron volts. Okay, you don't have to work hard. Okay, so work smart. Okay, so here we'll say it's 300. Okay, so we have used Hc as 1240 and divided by lambda in nanometers. Keep that in mind, and minus, so that is a short trick over here, minus work function 2.54. Okay, so you get this and this will get cancelled. 3 tens are 3 watts are 3 fours are 3 ones are 41.33. so that will be 10 divided by 10, so 413 minus 2.54. okay, this is in electron volts, right? So 4.13 minus 2.54, that will be 1.59, I guess. Yeah, that will be 1.59. so here you have 1.59 electron volts, and here you have E into V naught. Now you want the answer in SI unit, volts, right? You have to convert this to joules. No need of doing that, because here also you have E and here also. In order to convert electron volts to joules, you will multiply it by 1.6 into 10 to the power minus 90. And what is this? This E is charge on electron, 1.6 into 10 to the power minus 19. Okay, so this and this will get cancelled, and your answer is of course option D, 1.59 electron volts. Okay, forgive me for any calculation errors, if any. Okay, so your answer is 1.59 volts. Okay, did I say electron volts? No, your stopping potential is 1.59 volts. Okay, so that is your answer. Now one more question on stopping potential. You can try this. It will test how well you have understood the idea of stopping potential. Okay, so if the kinetic energy, the maximum kinetic energy in a photoelectric effect of a photoelectron is 2.5 electron volts, then what is the stopping potential? Okay, this is something for you. You'll tell me the answers in the comment section, and the correct answer will receive a heart from me. If the maximum kinetic energy in a photoelectric effect of a photoelectron is 2.5 electron volts, then what is the stopping potential? You'll also note a very amazing thing over here, and do mention that in the comment section as well. Okay, over to the next question. So question 6 and 7 over here, similar type of questions, so I grouped them together. Okay, so in question 6 you are given that the threshold wavelength for a photoelectric effect to happen is 2300 angstroms. The wavelength of the radiation is given over here. You can see that this is smaller, right? The wavelength of the radiation is smaller, so photoelectric effect will happen, right? Now don't confuse that with frequency. This is wavelength, right? So smaller wavelength means smaller than the threshold wavelength means the photoelectric effect will happen. Okay, so you are supposed to find the maximum kinetic energy of a photoelectron in this case. Okay, so again the golden equation, that is the only thing in this chapter, I guess. So yeah, So maximum kinetic energy will be given as E minus phi. E is the energy of the radiation. It will be given as hc by lambda, right? And this lambda will be this or this. It will be this, right? Of the radiation, right? The wavelength of the radiation, of course. And here also we'll have hc by lambda. But this lambda will be the threshold wavelength, right? It's related to the work function, right? So here either we have h into mu naught, which is the threshold frequency, or hc by lambda naught. Okay, lambda naught is the threshold wavelength. Now let's do it. Now you can see that here it is hc, right? Are you going to do it individually? No. Here you can see the answers are in electron volts, right? So we can exploit that. We can use hc as 1240. Remember? Yes. So we can take that hc common. So 1240, that will be 1240. And remember, place lambda in nanometers, right? Or you can substitute this as 124 and place that in angstroms. Okay, anyways, we'll keep it the standard way, 1240 divided by lambda in nanometers. Okay, so convert this in nanometers. It will be 230 nanometers and this will be 180 nanometers. Okay, right? I hope you got it. See, 1800 angstroms. Angstroms means 10 to the power minus 10 meters, right? This is 10 to the power minus 10 meters. Now I have to convert it to nanometers, so which is 10 to the power minus 9. So I'll kill this 0 with one of this, so that will give me 10 to the power minus 9 meters. Okay, so 180 into 10 to the power minus 9, so it is 180 nanometers. 180 nanometers. Okay, I hope that is clear. Let's come back over here. Now lambda, substitute lambda, which is 180 minus 1 divided by 230. Okay, excuse me, a lot of calculations over here. So after calculating, you will get the answer as 1.49 electron volts. Anyways, let's try doing it. So that will be 1240, 230 minus 180, that is 50 divided by 230 into, god damn it, that is so much. So this and this can get cancelled. 41.3 when you divide it by 3, and here you will get 6. Okay, we just did this previously, right? So 41.33. I can approximate this to 46. I know that is a very big approximation, but yeah, let's see what happens. So 46 into 5 divided by 23, because 23 can cancel that. Okay, basically that reason. And here you have 6. So 2 3s are 3 divided by 5 divided by 3, that will be 1.5 divided by 3. 3 2s are 6, so that will be 1.66. Yeah. So here we are getting a bigger value, okay, because we have made 41 to 46. Okay, we have increased the numerator. The value should be smaller than this, and the only value smaller than this is option A, right? So we are lucky enough to make this approximation over here. At least we can find the answer logically, right? So this answer should be less than 1.66 electron volts, right? The answer should be less than 1.66 electron volts because we increased the value in the numerator. So only answer less than that is option A. Okay, so option A is the correct choice over here. Again, the same thing in question 7. This is from 2010 now. So again, the same thing you have to do. So kinetic energy maximum equals, are we supposed to do it again? So let's directly substitute the values over here. Okay, so 1240, 1 divided by your 150 minus 1 upon 200. Okay, I directly place these values in nanometers. I know that 10 is going to get cancelled. Okay, so 1240 into 50, 200 minus 150, 50 divided by 150 into 200. I think this will be simple. This is 5 4s are 4, 3s are 12, 31 divided by 15. So that is, if you see, it's almost the double, right? 15 2s are 30. So that is approximately, I can say 2, right? Other values are very far. 1.5, no. Not this, not this. It can be 2. Okay, it is very close to 2 because it is in electron volts, right? It doesn't matter if it's 1.99. Okay, so that is 2 electron volts. Okay, so option A, 2 electron volts is the correct choice over here. Let's move to the next set of questions. So question 8 over here. In this question, you are supposed to find the de Broglie wavelength. Yeah, the pronunciation kills me. So find the de Broglie wavelength of a proton which has mass equal to this and which is accelerated by a potential difference of 1 volt. Okay, so let's do it. So de Broglie wavelength is given as h by p, right? And now as a physics student, you should know that the relation between your momentum and kinetic energy is under root 2 mk, right? Momentum is under root 2 mk, where k is the kinetic energy, of course. So lambda equals h by under root 2 mk. Now in place of that kinetic energy, you can write q into v, right? Same logics of work energy theorem. Okay, kinetic energy spent will be equal to the work done by the potential. Okay, so q into v. So in place of your kinetic energy, place that value 2mq into v. Now you have to substitute the values and get your answer. So h is 6 into 10 to the power minus 34 joule second, under root 2 m is 1.6 into 10 to the power minus 27 into, next is charge is 1.6, same as electron, into 10 to the power minus 19 and into 1 volt, right? Now you are supposed to solve this, and after solving it, the answer that you'll get is option B. Okay, no, I am not going to do this now. You can remove this 1.6 out from here. Root 2 is 1.4, and then you can play with the powers of 10 and you will get the answer. Okay, the correct answer over here after calculating that you should get is 0.9 into 10 to the power minus 12 meters. Okay, now some of you who wish to do it through digital math, please don't do it through digital math, because here they have used approximations, so the answers through digital math won't match. Okay, and for those who don't know digital math, this is for the people who hate math, okay, who hate calculation but love math. Okay, so something like that. So if you don't like calculations and if you want some sort of help in your BITSAT regarding this calculation thing, you can go check out the video on digital math. Okay, it will help you a lot. Okay, editor, yeah. So let's move to the next question now. So question 9 over here, it is given in this question that E1, E2, E3 are the kinetic energies of electron, alpha particle and proton respectively. They have the same de Broglie wavelength. Yeah, so you are supposed to do what the education system does to you, rank them. Yeah, no raising issues over here. Okay, let's solve this. Now first of all, some of you might think that the energy will be given as hc by lambda. They have the same lambda, which means all of this is constant for all three of them, which is h is constant, c is constant and lambda is same for them, which means that all three of them will have the same energy, which is in fact the wrong option over here. Okay, so why? Because here E1, E2, E3 are the kinetic energy. This is the energy of the radiation, right? We are having this misconcept over here. Okay, this is kinetic energy, this is energy of radiation. Okay, complete mess over here. Okay, so we are supposed to account for the kinetic energy. Now how can we write that? So first of all, we have to write kinetic energy in terms of your de Broglie wavelength, right? Something which we did in the previous question as well. We wrote lambda as h by p, then the relation between the momentum and kinetic energy, which is under root 2 mk, right? So you can see that your kinetic energy, okay, the under root of kinetic energy is under root 2 m into your lambda, right? Now h is same for all three of them, and also the lambda is same, right? They all three of them have the same wavelength. Okay, so you can directly see that your kinetic energy is inversely proportional to mass, right? When you square this, kinetic energy is inversely proportional to mass, right? So the lightest particle will have the highest kinetic energy. right? Which was obvious because lightest particle will travel faster, obviously, right? So kinetic energy is inversely proportional to mass. So the lightest particle, which is electron, E1, will be the highest, right? The kinetic energy of electron, the lightest particle, will be highest, followed by your proton. Proton is next lightest particle, okay, which is 1000 times heavier than this, okay. Then comes alpha particle, which is the heaviest among these three, okay. So E1 followed by E3, then E2, okay. So E1 is highest, E3 is the second highest, and E2 is the last, okay. So E1, E3, E2, that is how you rank them. Over to the next question. So question 10 over here. In this question you have an electron and a proton, okay. The electron has mass small m, the proton has a mass of capital M, okay. So basically we have used a notation for their mass, okay. So this both of these are accelerated by a potential difference of V. The de Broglie wavelength of the electron is lambda. Then express the de Broglie wavelength of proton in terms of the de Broglie wavelength of electron, okay. So you can give it a shot, okay. So we can see that the lambda will be h by p, okay. So the de Broglie wavelength we can write it in terms of the potential, right? I have been doing this since the previous question or the previous to previous question. So that will be p is under root 2 mk, and again in place of k you can write q into v, right? Hope no doubts regarding that. So you can see that the lambda is inversely proportional to your, now what are the things differing? It's inversely proportional to mass, potential is same, so when you take the ratio it will cancel out, right? So it's inversely proportional to mass, okay. That is the only thing that I can see, inversely proportional to mass. And charge for a proton and electron, it's same, right? Magnitude wise it's the same, okay. So charge is same, potential is same, h is a constant, 2 is constant, yeah. So your potential is, sorry, your wavelength is inversely proportional to the square root of your mass, okay. So we can write it as the de Broglie wavelength of proton divided by de Broglie wavelength of electron will be equal to under root, now inverse relation, right? So mass of proton over here, inverse relation, and mass of electron on top, okay. So the de Broglie wavelength of proton will be given as, now take this to the other side, de Broglie wavelength of electron, it is given as lambda. Mass of electron, it is given as small m, divided by mass of proton, which is given as, mass of proton, which is given as capital M, right? So it is lambda small m divided by capital M, lambda small m divided by capital M, okay. I hope you can make this out, it's capital M, okay. So option B, lambda under root small m by capital M, is the correct choice over here. I hope this is clear. Let's move to the next question, okay. By the way, this was the last question from the easy category. Time to step up the level now. Let's go to the easy moderate category, okay. So question 11 over here. In this question you have used a radiation which has a wavelength of lambda. You saw that the maximum speed with which the photoelectrons were emitted was v, okay. Now you have changed the radiation, you have used radiation dash, okay. So this has a wavelength of 3 lambda by 4. What will be the maximum speed of the photoelectrons in this case, okay. That is something which you are supposed to find. This is a good question, you can surely give it a try, okay. So let's do it. What are we going to use? We are going to use the golden equation, right? Okay, so kinetic energy in the first case will be given as E minus phi. Now in place of E, let's directly substitute it, hc by lambda, right? So hc by lambda, okay. Here the wavelength of the radiation is lambda and minus phi, the work function of the metal. Kinetic energy in the second case can be written as hc by lambda, lambda dash this time. The radiation has been changed, okay. So the wavelength is over here 3 lambda by 4. Basically you can actually think about this, okay. You can think that the radiation of the wavelength of this radiation is reduced, right? This was lambda, it is made 3/4, right? It is reduced, okay? So the radiation's wavelength is reduced, which means the energy of the radiation will increase, right? hc by lambda. Energy is inversely proportional to lambda. Wavelength is reduced, your energy will increase. So energy of the radiation will increase, and that will be reflected as increase in the kinetic energy of the photoelectrons, right? So in the second case, the kinetic energy will be more, right? So kinetic energy more, which means the speed will be more, okay? Keep that in mind, the speed in the second case will be more, okay? So minus. So kinetic energy in the second case is more than kinetic energy in the first case. That is the point I want to tell, okay? So minus work function, same metal, so work function has not changed. Can I write it this way, that kinetic energy in the first case, now nothing of work function is mentioned as such, so I'll use the inequality. We'll see it is hc by lambda, okay? I removed that 5 from there. I hope this is clear. Suppose let's take values, this is 5, this is 1, so 5 minus 1, that will be 4, right? Now if I remove this 1, you can easily see that 5 is greater than 4, right? So that is what I did over here, okay? You can see that something has to be subtracted from this in order to make it equal to kinetic energy, which means this term is bigger, of course. So this term is bigger than the kinetic energy. Similarly, you can write it over here that kinetic energy in the second case is less than h4hc by lambda, right? Now you can take the ratio, but keep in mind that it is inequalities over here, so you have to take care of that, okay? So k1 by k2, okay, let's use this inequality, let's see if it's correct, okay? So it will be hc by lambda will get cancelled, so 1 upon 4 by 3, right? 1 upon 4 by 3. Now you can see that k2 will be, just let's verify this first, okay? So k2 is, let's k2 take it to the other side, and k2 is greater than k1 into 4 by 3, right? So k2 is greater than k1 into 4 by 3, right? So kinetic energy is greater than kinetic energy of the kinetic energy in the second case is greater than the kinetic energy in the first case, even if it's multiplied by a number greater than 1, okay? This is greater than 1, right? So inequality holds. That is the basic thing that I wanted to show from here, okay? So the inequality is correct over here, okay? Now, so this can be written as k1 by k2 less than 3 by 4, okay? Now kinetic energies, you can write it as half mv square, right? And m is same in both the cases. Electron, right? Mass of electron is same, only thing changing is speed, right? V square, speed is changing, okay? So we can write kinetic energy as directly proportional to v square, so v1 by v2 the whole square, okay, that will be less than 3 by 4, okay? Now let's do this. So that will give us v1 is less than under root 3 by 4. Okay, we want it for v2, right? We want the value of v2 over here, maximum speed in the second case. So v2 take it to the other side, v2 square will write is, that will be greater than 4 by 3 v1 square, or you can write it as where can I write it, v2 is greater than under root 4 by 3 into v. v1 is v, right? Speed in the first case is v. So your speed in the second case is greater than the speed in the first case multiplied by under root 4 by 3, option D, right? The speed in the second case is greater, v2 is greater than v into under root 4 by 3, right? So option D is the correct choice over here. Here you have to keep in mind that you are working with inequalities, so I did that verification step over there, okay? So that was important, because if you take k2 by k1, the inequality will reverse, right? So yeah, So option D is the correct choice over here. Let's move to the next question. So question 12 over here. In this question you have an electron, mass is denoted by m. It is placed in a constant electric field with initial velocity 0. Okay, you are supposed to find the rate of change of lambda with respect to t. Lambda again is de Broglie's wavelength. Okay, so find d lambda by dt. Okay, that is what you are supposed to find. So your de Broglie wavelength is given as lambda is equal to h by p, right, or h by mv. Okay, so h by mv. Okay, here let's find the final velocity. Okay, velocity at instant t. You can see that this electron is placed in an electric field. There will be force on this electron. Suppose the electric field is in this direction. Okay, force on electron will be in this direction, minus EE, right? So you have the force on electron as Q into E. Okay, that will be E into E, of course negative. Okay, now you can write that force as mass into acceleration. So mass into acceleration into minus E, that will give you acceleration as minus E by m, right? Some of you might directly know it as a result from electrostatics that acceleration on an electron placed in the electric field is minus E by m. Okay, so now we found out the acceleration. We can find the you can see it is a constant acceleration, right? So we can use equation of motion and find the velocity at an instant. Okay, suppose at a instant t. So v is equal to u plus at. U is 0, a is minus E by m into t. A into t, right? V is equal to u plus at, u is 0. Now we have the velocity at an instant. Substitute it over here, differentiate with respect to time, and that is how you'll get your answer. By the way, there is one more way of doing this question. You can see that they have messed up with the terms, right? So you can use dimensional analysis over here. Anyways, we are doing it by the conceptual way. So h by when you multiply m and v, so m and m will get cancelled, right? This m and this m will get cancelled, and you'll be left with minus E by t. Okay, so now you have to differentiate it with respect to t. So differentiation of 1 by t is minus 1 by t square. Okay, everything else is a constant, so this will be minus 1 by t square, so that will make it plus. Okay, so h by t square. Some of you will get the minus sign. Don't worry, we are just concerned about the magnitude. Okay, so lambda is h by lambda by d lambda by dt. The rate of change of your de Broglie's wavelength with respect to time is h by t square. Okay, so option A is the correct choice over here. Okay, so yeah, that's it from question 12. Let's go to the next question, question 13. So question 13 over here. In this question you are given that the momentum, if the momentum is changed by p, then the de Broglie wavelength changes by 0.5%. Okay, you are supposed to tell what is the initial momentum. So today you can see a lot of composition, especially the concepts with the concepts of de Broglie wavelength, right? De Broglie wavelength can be mixed up with anything which has to do with momentum. Okay, so where there is momentum, there you can apply your de Broglie concept. Okay, so you can see a lot of composition in this chapter. Okay, so let's do this. So we are supposed to find the initial momentum. Now this is mixed up with error. Okay, your chapter 1. Yeah, so okay, so we'll write lambda is equal to h by p, right? So delta lambda by lambda is equal to delta minus delta p by p raised to minus 1, right? So basically if there is an increase in this, there will be a decrease. Minus sign basically shows that, right? So h is constant. Okay, so that won't come. This delta h by h, there is no error in h as such, so that is taken as 0. Okay, so this is the relation that we are going to use over here. The change in your relative change in lambda, here it is given percentage change, right? So let's make it relative. So 0.5 divided by 100. right? 0.5% means 0.5 divided by 100, and that will be minus p by p. Now this is initial lambda, this is initial momentum, right? Change divided by the initial, that is what relative is, right? So minus p delta p, what is the change in momentum? It is p. P is a certain factor, okay? So change in momentum is p, and initial momentum, this is what we are supposed to find. So yeah, it is a very simple thing, just made it to the easy moderate category because it is composition, okay? So 100 divided by 0.5, 100 divided by half, so that will be multiplied by 2, right? 100 divided by half multiplied, that will be multiplied by 2, so 200 into p, right? So that will be 100 divided by 0.5, so 0.5 goes on top as 2, okay? So the initial momentum is 200p, okay? So option A, 200p is the correct choice over here. Over to the last question for the day, okay? So question 14 over here, the last question for the day. In this question, you have used an X-ray radiation of 0.5 angstroms wavelength. So photoelectrons are emitted from the metal surface, okay? So these photoelectrons move in a circular path in a magnetic field as shown. So again, composition of concepts, right? So the radius of this path is given, the magnetic field intensity is also given. You are supposed to find the phi. Phi is the work function, not the flux. Find the work function of the metal. Now this data seems a bit weird, right? It is a scattered data. You are given the magnetic field, the radius of the circular path, the wavelength of your radiation. You are supposed to determine the work function, okay? What are we going to use? We are going to use the golden equation, okay? So that is the only thing that we know in this chapter, and of course de Broglie wavelength, yeah? So kinetic energy maximum will be E minus phi, okay? Now what can we use? Now we have to find the work function, right? So work function will be given as the energy of the radiation minus kinetic energy. Now we can find the energy of the radiation. What about the kinetic energy? So the thought process is involved over here, okay, in finding the kinetic energy. We can find the energy of radiation from this. We can easily do it. Energy will be hc by lambda, right? Hc, we can use the trick which I said, 1240, and lambda in nanometers, right? So 0.5 and one more, so that will be 5 into 10 to the power minus 2, okay? So 1240 into, I can write it as 100 divided by 5, 5 2s are 0s are, and that will be 2 zeros 100, just a bit of maths, 248 into 100, okay? So that that many electron volts energy we have, okay? So now the next thing, how to find the kinetic energy, okay? How will you find the kinetic energy? You can write kinetic energy as half mv square, okay? This is fine, half mv square, okay? What is the next thing that you can do? We don't know anything about your velocity. First of all, you can tell me why is this moving in a circular path, okay? Why is it so? So just think about this, okay? Let's go back to the story, okay? It although it's not important over here, but yeah, let's go back to the story. It's worth mentioning over here, okay? So first of all, the radiation falls on the metal. The photoelectrons come out. The photoelectrons come out with certain kinetic energy, right? So with some amount of velocity, with some speed, right? So they are moving with a speed. So we have a moving charge, an electron which is moving. So moving charge in a magnetic field which is perpendicular will make a circular motion, right? So that is why it is making circular motion. Anyways, let's get back to this now. What are we supposed to do? We are supposed to find the velocity, okay? We know the mass of the electron. What about the velocity? Let's think about velocity. What can we do? They have given us this data, right? The radius is given. So can you recollect that the radius of such a path in a magnetic field is given as mv by qb, right? mv by qb, okay? That's nice. So here you can find the velocity using this, right? You can find the velocity of that electron. So it will be qbr okay, QBR by M. QBR by M, that will give you the velocity. So you can substitute it over here and you'll get half, or else I write it as q square b square r square, right? In place of v, we have q square b square r square divided by m square, and this m will get cancelled, and we have q square b square r square, whatever the radius is, r square divided by 2m. This is the formula for kinetic energy. Okay, you might have also learnt it in I think electromagnetic induction, wherein you prove Lenz's law. There somewhere you might have learnt it, that kinetic energy is q square b square r square by 2m. Okay, we derived it from here. Now you have to substitute the values, and you know where this is heading to. I'm not doing it. Yeah, so 24800 minus q square b square r square. So q square, q is charge on electron, which is this, b square, this square, so 4 into 10, b square is 4 into 10 to the power minus 2 square, that will be minus 4, r square 23 millimeters square, so r is 23 millimeters. Okay, and m, the mass of electron, which was not given by the way, so it is 9.1 into 10 to the power minus 31 kgs. Okay, so yeah, so here you'll substitute all the values, get the kinetic energy. Suppose it is x, so you subtract x, and whatever answer you get, that will be your answer. Okay, I think if I'm not wrong, okay, the correct answer over here should be 6.2. Let me just check it. Yeah, it's 6.2 electron volts. Okay, so 6.2 electron volts is the correct choice over here. Yeah, that's all for today. We'll move to your homework question, and yeah, we'll wrap up with the class. Okay, I hope you understood this. So question 15 over here, this is your homework question. You can pause the video now, take a screenshot if you wish to try it later. Okay, so do let me know the answers in the comment section. The correct answer will receive a heart from me. Okay, so I know this is a bit calculative one. Okay, you can go watch the video of digital math now if you are in a fresh mood to do so, because that will help you in your calculation, in speeding up your calculation for BITSAT. Okay, so I'll suggest it at the end of this video, so you can do check that out. It's a very nice video. That video has a fan base of its own. Okay, so yeah, that's pretty much it for today's class. And I also know that the playlist is getting disordered. Okay, lectures are made randomly over here. Someday I come and teach electromagnetic induction, other day I come and teach photoelectric effect. So I know the order is getting, the playlist is getting disordered, but I'll line it up for the future aspirants. Okay, now the aim for 2021 is just to complete the series right before your BITSAT. So the lectures will be random. Okay, any chapter can come anytime, but yeah, we'll hopefully try to complete the A series before your BITSAT 2021. Okay, so that is the aim for future aspirants, for aspirants of 2022 or others. I'll make a different playlist where I'll keep the order very nice, okay, according to your NCERT. So yeah, that's pretty much it for today. I hope you enjoyed this lecture. If you did enjoy, smash like, subscribe. I'll see you soon in the next one. Keep enjoying physics.